All right, guys, as you can see on the board, I just finished number 6 on 5.3, and I'm going to go over number 7. Let's go ahead and erase all this. There are 2 major differences. Well, okay, 3 major differences between number 6 and number 7. The first is the presence of another force outside of kind of your standard of gravity normal friction. The second one is they split it up for you. You don't have to actually split it up to do this problem in full, although it can be a little bit more confusing that way, which is why the problem is split up. The third major difference is the fact that they make you go find force friction using stuff from the last chapter. I am going to skip that section, okay? I'm not going to talk about how to find that force friction. If that is your biggest issue here, then we can tackle that issue separately, because I'm going to mostly focus on the energy part of this. So when I get to that part where I'm finding force friction, I'm just going to say, hey, this is where you would go do this. If that's your trouble, let me know. All right, so we have a hill, okay? And the angle of that hill is 15 degrees. There is a box being pulled up the hill. That could be by an engine, that could be by a person, who knows? But it does tell us, they call that force of push. Now, whenever a problem gives a name to a force, I usually try to use that name myself to avoid confusion a little bit later on, okay? Other than that, we know that the hill, of course, is going to push perpendicular with force normal, back the opposite with wave force friction, and straight down with the force of gravity. Let's go ahead and put up our given. It tells us that the box is 10 kilograms. It tells us that the velocity initial is 1.5 meters per second, as opposed to at rest, which problem number 6 was at. It tells us mu k is equal to 0.4. That's specifically going to be used for finding force friction. And that the total displacement that it's going to go through is 7.5 meters. What it specifically we're going to find is, of course, separated by the individual parts. But it will tell you that usually when you get to the end of the chapter, the main thing that it's usually going to have you find is either the displacement or probably this, the final speed. So I'm going to go through it part by part, but ultimately, usually they're put all together here at the same time. So part A. Part A asks the question. I would know better if I had not have lost my place. My apologies. 2 seconds here. Okay. What is the work done by gravity? We always calculate work the exact same way. That's going to be force of gravity times displacement times cosine theta of gravity. As you saw in potentially number 6, if you didn't do this, of course, if you don't want to write force of gravity, if instead you want to write mass times g, that's completely fine, with one major caveat. Then we can do this because it gave us mass. Sometimes later in the chapter, problems are just going to straight up give you force of gravity. Obviously, then just don't put mg. And we're going to go straight to plugging in. Mass is 10 kilograms times g. Displacement is told to us at 7.5 meters. And the hardest part of this, again, is going to be the angle. Well, the angle is measured between the displacement, which is going up the hill, and the force. So that's going to go from here all the way up there. Now, here's how you can do this. From the vertical to the horizontal, we know is 90 degrees. So how much more angle is it to get up? Well, that's easy. That's just 15 degrees. So our angle should be 90 plus 15, or 105. Let's go ahead and plug that in, and we should end up with negative 190.2 joules. It should make really good sense in this case as opposed to the last one that gravity is negative, because you're going up a hill. So gravity is fighting the overall motion of the object. It should definitely have a negative answer. Part B says, what is the work done by friction? Well, this is going to be force of friction times displacement times cosine theta of friction. And there's this spot where I say, This is the part where finding force friction is stuff from last chapter. I'll give you a hint in that you are definitely supposed to rotate the axes to do this, to go get force normal first and then to find force friction. But once you've done that, what friction that you should get here is 37.9 newtons. Again, if that's your issue, please let me know. But displacement is still 7.5, and the cosine is at 180 degrees because the angle is from displacement, which is up the hill, to the force, which is the opposite way, 180. So that, of course, is going to end up as -1. And my total work done by friction is negative 284.0 joules. Again, making sense that it's negative because it's taking energy out. Part C, probably the easiest one we have here. We need the work done by the pole, this force done by the pole times displacement times cosine angle of the pole. The force is 100 newtons, the displacement is 7.5 meters, and that angle is 0 because they're going the same way. Regularly throughout this, you might have been confused because you might have thinking I'm getting the angle between this force and force of pull, and that's not accurate. I'm getting from the displacement, but they are all both going up the hill, which is why this is 0. So that's just 1, giving us a work of 750 joules. Now, part D. Part D asks specifically, I want to make sure I don't get this wrong, what is the change in kinetic energy of the object? Now, it's a little bit different than everything we've been asking so far until you realize the work kinetic energy theorem is the work net is equal to the change in kinetic energy. So that's just another way of asking for what is the work net. Since we have all of the individual works, this is simply going to be equal to all of the works added up. If I look at my force diagram, I have work of pull plus work of normal plus work of friction plus work of gravity is equal to the change in kinetic energy. Let's see, make sure I didn't go off. Yes. Now you'll notice I only calculated 3 of those and I have 4 of them up there. Hopefully you've already recognized that work normal is in fact 0 because they're at 90 degrees. So literally just add up the 3 answers that I have prior. Work of pull, it said, was 750 joules, plus work of friction was negative 284 joules, plus the work of gravity is negative 190.2 joules. Added that all up, and that is equal to, what I got, positive 275.8 joules. So there's a positive work, there's a positive change in energy. We should expect this thing to go faster. The final piece of this is how fast is it going at the end? Now you'll remember that what I said is that ultimately that's usually what is asked at the very beginning. Basically, the way to do this without parts is start up here, and then after you've done this piece right here, let me make sure I'm not missing anything. Yeah, there we are. Once I've done this piece right here, instead of plug their individual answers in, you of course would plug in their individual equations in. Now that gets big and messy. So if you do prefer to kind of do it step by step, you certainly can and do it this way as well. This is equal to work net, which is also equal to change in kinetic energy, and it wants the final speed. So the other thing to do here is change in kinetic energy is kinetic energy final minus kinetic energy initial. In problem 6, kinetic energy initial dropped out because it wasn't moving at the beginning. Here it doesn't drop out because it is moving 1.5 meters per second at the beginning. So let's go ahead and fill in. That guy is this. So I'm going to solve for KF. If you want to go straight to plugging in your equations, you can. It's just a little bit easier to move them before you fill out all their equations. There we are. And we have 1/2 mass velocity initial squared plus the change in kinetic energy is equal to 1/2 mass velocity final squared. Like I've talked about quite a bit already, you can't cancel mass here because you have one in the first term and the last term, but not the middle term. You cannot cancel 1/2 for the same reason. Now you could do them, they're just going to show up on this middle term. As a matter of fact, why don't I go ahead and do that? Let's multiply everything by 2. That's going to put a 2 in front of this and cancel it here and here. Let's divide everything by mass. which is going to divide that by mass. And then this is just going to be VI squared plus that whole mass is equal to VF squared. So I do need to square root that to get the final speed. Just a quick piece of advice, that does not cancel that squared because that is added. So you do need to plug all of that in. The VI is 1.5 meters per second. I apologize for the small space. Plus 2 times the kinetic energy is right here, 275.8 joules, divided by the mass of 10 kilograms, square root the whole thing. And if you have done this correctly, you should end with a speed of 7.58 meters per second, or about 7.6 meters per second. And that's how you do that problem.